In the introductory video, we saw what is a qubit and the block sphere representation of it. But the question is how to realize a qubit physically. Take for example of a classical bit which is realized physically as a level of voltage across a particular element representing the bit in an electrical circuit. So in this video, we'll see a system which can correlate with the properties of a qubit. So in 1922, Stern and Gerlach performed an experiment with the neutral silver atom which was heated in the oven, and the beam of this silver atom was passed through an non-uniform magnetic field which caused the atom to be deflect. Now, in 1927, the same effect is observed with a much simpler hydrogen atom, which only contains a single proton and an orbiting electron. Now we know electron orbiting around the proton causes an electric current, which in turn creates a magnetic dipole moment, which is analogous to a tiny bar magnet. Now, when these atoms with tiny dipoles are thrown into an external non-uniform magnetic field, they are deflected by the field. And since the dipole moment, that is mu, which is given by this expression, depends upon the total angular momentum j, which is the sum of orbital angular momentum and spin angular momentum, that is j equal to L plus S. This implies that the magnetic dipole moments are quantized and the deflection we observe are discrete. This fact was not known at the time of the experiment. And since the atoms emerging from the oven had random orientation of dipole moments, it was expected that there would be a continuous distribution of atoms seen at all angles. But the actual result was different. The two beams, one deflected up and the other deflected down, was explained by the property of spin of electron in hydrogen atom, which we all know in today's time. So now let's represent the output beam with the state plus z and minus z, since the deflection was in z direction. Now if we cascade two Stern-Gerlach experiments together, that is pass the plus z output with another Stern-Gerlach apparatus, that is a non-uniform magnetic field, along the x direction. That is, this apparatus had magnetic field which was non-uniform along the z-axis, and this apparatus will have magnetic field around the x-axis. Also, will block off the minus z output. Classically, magnetic dipole pointed in the plus z direction has no net magnetic moment in x direction. So, we might expect the final output to be one central peak. However, experimentally, it is observed that there are two peaks of equal intensity, which we'll name as plus x state and minus x state. So, the atoms passing through the second apparatus can be described as being in a state we might write as plus z plus x for this beam and plus z minus x for this beam to indicate the two values of spin. Now again, by sending one beam, that is the plus x state, and blocking of the minus x state through a third apparatus which also has a non-uniform magnetic field in z direction. This is to check that whether the atoms have retained the plus z orientation or not, so that we would expect the output to have one peak of plus z beam. However, again, two beams are observed at the final output of equal intensities. Therefore, we conclude that the plus z state consists of equal portion of plus x and minus x states, and the plus x state consists the equal portion of plus z and minus z states. Now, similar conclusion can be reached if the apparatus is oriented in the y direction. Now, we can implement the qubit model to explain this experimentally observed behavior. Let us assign the 0 state to plus z output and the 1 state to minus z output. And since plus x state and minus x state are equal portions of plus z and minus z states, plus x state can be written as 0 plus 1 by root 2 and minus x can be written as 0 minus 1 by root 2. Conversely, we observe from the second and third apparatus that plus z and minus z are also equal portions of plus x and minus x state. Therefore, from this we can see that plus z is equal to 0 state, which can be written in terms of equal portions of plus x and minus x, which would be equal to plus x plus minus x by root 2, which would eventually give us 0 state, and minus z can be written as plus x minus minus x by root 2, which would eventually give us the 1 state. This also implies that the Z Stern-Gerlach apparatus measures the spin in the computational basis 0 and 1, whereas the X Stern-Gerlach apparatus measures the spin with respect to the basis 0 plus 1 by root 2 and 0 minus 1 by root 2. Also, the probability of getting the plus Z state from the third apparatus is half, and the probability of getting the plus x state from the second apparatus is also half. So this example established that the qubit model is the correct way of understanding electron spin, and also generally how qubits could be a way of modeling systems in nature. So I hope you understood how we can physically realize a qubit state.